So I was asked to go over I think the last problem. So let's pull up what I have here. Um, page one. This was the distance problem between point to a plane. Need to rotate that. Take the second one. Unfortunately, I don't. I have a PDF maker here, I guess, on this machine, but I didn't have it on my other machine. So it's not allowing me to rotate. So let's go to this problem. Still not allowing me, so let's open it in a different viewer. And then rotate that. Okay, let's take a look. So you're supposed to find the shortest distance between a point and the plane. And these points might be different for you. The plane I can solve for z, so it's z equals 4 minus x minus y. And if I have an arbitrary x, y, z on the plane, then I can actually calculate the distance between the point to the plane by the distance formula. So any arbitrary x minus 1, because I'm taking these two, y minus 0, and z minus the minus 4 under a square root. So and for z, I'm going to put in the formula for z, which is 4 minus x minus y. So that gives me an f of x, y that I'm supposed to try to minimize. And I don't want to work with a square root because that's going to give me a nasty chain rule with a 1/2 blind side to the minus 1/2, so all kinds of stuff. So the first observation is that I don't have to work with the square root. I can just work with the square because finding the minimum or the maximum of a set of numbers, let's say if I have 1, 2, 3, the location of where the max occurred here, it occurred in the third number here, and it also occurs in the third number here when I square them all. Similarly, the minimum occurred at 1, and it's at the same location as the minimum here in the number squared. So finding the location of the minimum of a set of numbers is the same thing, is at the same location of the square root of those numbers. So this means that I don't really have to worry about that square root. I can just find the location of the minimum using the square, and that drops out the problem that I have with the square root, which it's doable that way. I guess you could get on Mathematica and just do it. It's no sweat off your back, right, if you do it on Mathematica. But I did this by hand, so I think I did a piece of it on Mathematica. So here's my, first I take the derivatives, derivative with respect to x, derivative with respect to y, and then I set them equal to 0, and I put them into Mathematica because I was lazy. So I set gx equals 0 equals gy. So I set two equations equal to 0 and asked Mathematica to solve them. And I got x equals 10 over 3 and y equals 7 over 3. Only one critical point. If you read the problem, they actually want the distance. So you have to go back to the original function, not the square function. That's the distance, and put in the x and y you found into the formula. And I got 7 over square root of 3. And as Connor would say, I put it in a WebAssign, it was the right answer. So that is true, but there's still more work to be done. We still have to check that this is a min. So we find the Hessian matrix, and I'm working with gx, the g, because I don't want to deal with the square roots. and I find the second derivatives. I already had the function on Mathematica, but their second derivatives are all nice. They're constants. So I got 4, 2, 2, 4 for these second derivatives. And then I just told Mathematica to find the eigenvalues, and I got 6 and 2 as the eigenvalues. They're both positive. So this is a concave up model, so that this is a minimum. So I hope that helps on this problem.